So today we will talk about recommender systems. I'm sure that all of you have heard about Netflix challenge, where the goal was to be able to predict which movie the user would like to watch. So this type of problem are called recommender problems, and almost every single e-commerce website uses recommender algorithms to advise you on which product you may be interested in. So today we will cover the technologies that enable machines to learn this type of preferences based on the prior choices that the user have made. So we will start today's lecture by looking at first the problem definition, and we will see that there are many ways to think about this problem definition. Next, we will take an approach which would be very simple approach, and historically this was the first generation of recommender algorithms, and this approach is called k-nearest neighbor algorithm. And finally, we will talk about the approach which is prevalently used today, and this will be most of our lecture, and the approach is called matrix factorization or collaborative filtering. Okay, so let's start with a problem definition. So I will first introduce the notations that we will be using throughout the lecture, and following the idea of Netflix, just to make it very concrete, I'm going to be talking about users and movies. So imagine to yourself that you have a very big matrix. Here you would have all possible users in your system. So we would assume that we have n users, okay, and we will have m movies. Okay, so this will be n by m matrix. And the name we would call this matrix is going to be matrix Y. And when we are looking at particular element AI, we are looking maybe at user A, and here's the whole preference for movie I. So UAI would remember how the user rank particular product. And in this case, you can say, some website allow you to put, number from 1 to 5, other one you can do thumbs up, thumbs down. There are many different ways to define it. For us, we would just assume it's some continuous number. It doesn't matter, you can always translate it to the scale you want to have it in. So now, if we're going back to the Netflix problem, which actually brought this big question to a broad machine learning community, the goal was to make this prediction based on prior choices of the users. And in the case of Netflix challenge, they look at 500,000 users, so our N was 500,000, and the number of movies was 18,000 movies. The interesting part about it, that most of this matrix is actually empty. It's a very sparse matrix. On average, each one of the movies is only ranked by 5,000 users, 5,000 out of 500,000. So most of this matrix will be empty, and here and there you would have the rankings of the users that already watched the movie. And now the goal of the algorithm is actually to fill out the whole matrix. So that now, let's say, there is some user 1 and the movie 1, which we originally didn't record the number for that user. We want to somehow predict what will be the opinion of this user for the movie he or she hasn't seen. And the question is, how can we address this problem? So the first thing that some of you are already thinking, based on our previous linear regression lecture, say, oh, this is really a regression problem. Maybe what I can do, I have my movie, I've seen how this user ranked previous movies, and now based on the features of the movies, I can predict the ranking. That's what we've done in supervised learning. We just think about feature vector, maybe, you know, who participated in the movie, you know, was it European movie, did it have happy ending, whatever features you want, you represent it as a feature vector, and then you use regression to predict the scoring of this movie. However, the approach that I will show you today doesn't relate to traditional supervised learning directly. And there are several reasons why we may not want to use the regression here. So the first reason is that our assumption is that we know what features actually determine the ranking, and that we can automatically extract those features. So you can say, I can take my features from IMDb. You could, but IMDb doesn't record whether this movie had a happy ending or not, and maybe for that particular user this is really important. And if you're thinking about like much bigger matrices, like, you know, Amazon, all the different products that are in Amazon, it's really not clear what features are we going to record, and it will be really huge feature vectors. The second problem is that in order for us to do linear regression for a specific user, we actually need to have enough rankings of this user. So if we just have few rankings, we would be unable to recommend this user any new products. So given these two limitations, we will take a different approach. And the key idea of this different approach is that we can recommend the product to our user, but identifying his or her similarity to other users in our pool. Because maybe you're assuming that there are people who are similar to me in some way, I should be able to borrow the ranking of users who are similar to me to predict my own ranking. So with this idea in mind, we will start by looking at the first algorithm for predicting recommendation, and this is called K nearest neighbors. Let's write it down. K nearest neighbors. Okay. So the number K here means how big should be your advisory pool, on how many neighbors you want to look at, and this can be one of the hyperparameter of the algorithm. Let's say here we have some user who didn't watch. Let's start with our first user. That user didn't watch the first movie, but maybe they watched some other movie. So here this user gave 5, here they gave 4, and here they gave 1. We may have some other users who did watch this movie, gave to it also 1, and gave 4, 4, and 2. We also have some other users who, let's say, liked everything. You know, there are some people who love everything. So you can look at this particular thing. So maybe here they also like some other movie. Let's make them very happy user. So you can clearly look at these two representations of the user, and here we are representing the users by their choices and say that actually my user is closer to this specific user, and maybe because this user predicted 1, I can give the same score, and maybe it could be some low score for my first user for the first movie. Now, in reality, you may not want to use just a single user. Maybe there are many other users who are similar to me, and I'm going to aggregate them all and look how did they score the movie that I'm interested in and take their average. This is our first idea. So what we will do, we will say, okay, and I would use the following notation. YAI, and Y with the hat means predicted Y, predicted value. I am going to go now through all the users B, okay, which are my K nearest neighbors, okay, of me, of user A, who did watch movie I. So I'm going to select all the nearest neighbors who did watch this movie, take their score for that movie, because we know that they watched it, and then divide by K. So what we pretty much wrote here in formula, it's exactly what I said in words. We will identify users similar to me, take their values and take their average. Now the question you may be asking is, how do I define the similarity? And we already discussed there are many ways to compute the similarity. You can use cosine similarity, you can use Euclidean distance, because at the end every user is just a vector, and you can use any measures that you've seen in this class to compute the similarity between the user vectors. Now, some of you may be saying, okay, let's say I want to have k large, and some users are really closer to me, and some users are farther away from me. You can get even more sophisticated, and you can say, okay, I'm not just gonna take the score of that user, but I want to weigh it by how similar this user is to me. We can easily do it. We can just say, okay, in this case, we assume that we have similarity score, and we will look at k nearest neighbors. But now when we are taking their score, we will actually compare the similarity between A and B, between me and this user, and use it as a weighting factor. And now we will divide it by the sum of all the similarities. So in this case, you can see that there are many ways to go, and people at the time when these algorithms were popular designed a variety of metrics. Like for instance, we can say that if the user, maybe we as users, and actually people found that this is true in practice, that our median kind of what is my basic score differs from user to user, meaning that maybe I think that movie that is okay, I should just give to it 3, and I would give 5 to some super exceptional movie. The majority of movies that I like, I give to them 3, while somebody else may give to vast majorities of movies 5, like this happy user, and only if they don't like something they would give to it 4. So what people have done to that, they actually compared not the scores themselves, but how you deviate from your average score. So instead of using the original matrix, you would take an average score and record your deviation, either positive or negative from your average, and then you compare. So there are lots of different heuristics how people try to approach this problem, and they produce some okay results, but they're very far, all these techniques, from the state-of-the-art methods. And the question is why? So clearly, the goodness of this method would depend on how do you compute the similarity between me and somebody else. And it can be cosine similarity, it can be any other similarity. But the problem is that if you look at people, like look at me, I may buy some books in machine learning because this is an area that I work in, but I can also buy a book on plants because I really love plants. So how many people do you have which would have the same taste both in plants and in technical books like me? Maybe not that many, but there clearly will be people who would buy the same machine learning textbooks, and also people who are interested in gardening. So the idea is that this method doesn't enable you to detect the hidden structures that is there in the data, which is, I may be similar to some pool of users in one dimension, but similar to some other set of users in a different dimension. So when we are moving from k nearest neighbor, we are going to go to this new approach, which goes by the name collaborative filtering or matrix factorization, where the algorithm would be actually able to detect these hidden groupings among the users, both in terms of products and in terms of users. So then you don't have to engineer very sophisticated similarity measure. Your algorithm would be able to pick up these very complex dependencies that for us as human would be definitely not tractable to come up with such measures. So now we are ready to start talking about the next approach, which is called matrix factorization. So right now we will start talking about collaborative filtering. This is actually the main part of today's lecture. So let's write collaborative filtering. So now I want to start thinking about this problem in the same terms as what we've done when we were talking about supervised learning. You remember what we have done there? We were saying we have some objective and we want to optimize this objective. So what I would like to do is to say, okay, let's just think about the problem of recommending product as a standard kind of objective-driven algorithm. So, as I've said earlier, we have, and I will redraw it here so that you can see it better. This is our matrix Y. And the matrix Y, again, I'm going to write N and M. This is our users, this is our movies, and this is matrix Y. And I'm going to write here so that you don't forget, this is what is given to me. This is a matrix which have very few sparse entries, okay? The very few entries is a sparse matrix. Now I would say the goal of my computation is to build another matrix, which I would call X, okay? They're supposed to be similar matrices. X, okay, of the same size, N and M. And this is the matrix, which would be the output of my algorithm. This is the output. That's what I want to output. And here I want to have every single entry full, okay? Everything have to be completed here. So you're given with some initial entries and the algorithm needs to output the matrix X, which will contain prediction for every single user and movie. This is your goal, okay? Now, if I want again to think about it in terms of the objectives, that's what we were discussing before, I can now say that we can look at the our empirical risk that we are trying to minimize. In other words, for each of such matrices, possible matrices, we need to know how good is this matrix, okay? Okay, so the first things that we can do, and you will see now something very similar to what you already seen in regression, because it takes the same spirit. The first thing that we want to do, we want to say, of course, our objective should record the fact that if here, let's say for this user, I had some prediction, if we are looking to what is in this matrix for the same user and movie, it should be similar, or ideally maybe the same, because for these field entries, we actually know the answer. So the first things that we are going to write, we are going to go through all the pairs of users and movies that belong to D. And D, I will just write you, D is will be all the pairs AI such that the entry YAI is given. In other words, we're saying for all the cases where you already know the answer, because the answer was given to you, whatever you have here, the loss should be minimal. You want them to be very close to each other. So we are going to write YAI minus XAI, okay? And I am going to be using here again the same as in regression, squared loss. So this term tells you I want to be very close to what was given to me. Plus, in addition to it, I want to do regularization, the same way as we've done in linear regression, where we don't want our parameters to become really unruly large, and we're keeping their norm close to 0. So in this case, this is our hyperparameter lambda, okay? And we are going to go through all the entries of the matrix X, and we want them, and we look at their square, and we want this norm to be minimal. So if it helps you, you can also write it like this. So this is our objective that we will try to minimize. So we go through all possible matrix X's, and we want to find one which actually makes this empirical risk the smallest. So how can we do it? Again, exactly the same way as we've done in linear regression. First of all, I want to notice that the way I formulated the problem, every single entry here is independent of each other. Whenever I'm deciding about the preference of the first user for the first movie and the second movie, there is no connection between them. So actually, I don't have to keep the sum. I can independently estimate each one of those xi's, okay? And the difference here would be the following: whether this xai actually part of the set D or not. Because for all those that are part of the set D, we will need to look at these two factors. For those which are not in D, we would only look at this factor. So let's just start on looking again. We will make an assumption that particular xi that I'm looking at, it belongs to D. Okay? So in this case, as I've said, what we're going to do, we will take jx of that ai and do the same thing we've done previously, which is just differentiate with respect to this xi. And there is no sum here again, because we're looking at one xi at a time. So we will take yai minus xai square divided by 2 plus alpha 2 xi squared. So now, if we to take this derivative, and you will do it as an exercise, what you will discover, you will take this derivative, make it equal to 0, do the whole computation, and you discover something really funny here. What you will discover that xi, in this case, would be equal to yai divided by 1 plus lambda. If you finish your computation, so we're going to take this derivative, it's a very simple derivative, make it equal to 0, and that's what you're going to get. If you do exactly the same thing with the case where ai is not part of D, which means that in this case you only need to look at the derivative of this factor and do exactly the same computation, which we will do as part of your exercise, you will find that xi is equal to 0. So see what had happened here. This is something really funny. When we did our estimation, we said for all the entries that you didn't know what the value should be, you just put zeros everywhere. And for those that you knew what the value should be, you actually corrupted the value. Instead of taking yai, which is the correct answer, you take yai and divide it by 1 plus lambda, and depending how much regularization you do, the more corruption you introduce. So the solution that you got here is even worse than what you had in the beginning. I mean, it's just if you just add trivially 0, you're going to get better numbers. So it doesn't make any sense. So there is something wrong here, correct? In this particular way of thinking about it, which we exported directly from our supervised learning problems. And the answer comes from the fact that what I've done here, and you remember when I start taking the derivatives, I told you we are going to take it for each entry independently. How many parameters do I have here? I have n multiplied by m parameters. And again, if you need to make it concrete for yourself, think about 500,000 users and 18,000 movies. It's a huge, huge number of parameters which are estimating on a very small number of entries. There is no dependence whatsoever between different assignments that we are making. We are treating every choice independently. And it is not surprising that since we are not modeling dependency in any way, we are really losing important connection, which was the first reason why we decided to look at this problem differently in order to find the connection, the hidden connection between different users and between different products. So the problem with the approach that we discussed previously is that there is no connection between assignment of values for all the different entries of X. Whatever selection you are given for the first user for movie number 20 and 25 have no connection. We don't discover any groupings between either users or movies, and this was our main goal when we decided actually to look at a different approach. We wanted to discover all these hidden groupings. So what we want to do now is to somehow tie all these parameters, not to do independent estimation, and it's very crucial here because we don't even have enough training data to do this estimation, since we have so many parameters, 500,000 multiplied by 18,000, and very few entries for which we know the values. So ideally we want to decrease the number of parameters. And the way we will be doing it here, we will make an assumption, and this is our assumption. And this is assumption that our matrix X is low rank. So what you remember from linear algebra, that, you know, intuitively speaking, rank captures how much dependency do you see between the entries of the matrix. Let me start with maybe the simplest case, when we are looking at the case of the matrix of rank 1. Okay, so let me show you an example of such matrix. Let's say here we have a matrix which does 1, 2, 3, 5, 10, 15, okay? So this matrix can be rewritten as a multiplication of two vectors, 1, 5, and 1, 2, 3. Now, you can say, maybe it can be, it doesn't mean that we have the unique factorization. For instance, we can also rewrite it as 10, 50, and then 0, 1, 0, 2, 0, 3. So there are many ways to factorize this matrix, but what is important for us, that we actually can do it, because not every single matrix can be written in this form. As part of your exercise would be to come up with a matrix which doesn't have rank 1, which is the vast majority of the matrices out there. Now, why is it interesting for us to factorize, and how this idea of being able to factorize relates to our main goal, which is to decrease the number of parameters? This particular matrix, if you bring it back to our n and m story, has n multiplied by n parameters, okay? N by m parameters. Now, once we did this factorization, now this vector would have n variables, and from here we have m. So overall, we are having something n plus m different parameters. In reality, it's m plus m minus 1 due to this normalization issue. But what is important is that we are moving from n multiplied by m to n plus m. And whenever we are making this assumption that we are operating in case of rank 1, we are making very, very strong assumption of how the decision of users and their preferences on movies, how they are related. So let me just explain you intuitively, okay, what exactly these vectors capture. So we would call this vector u and this vector v. And my matrix X would be just a multiplication of vector u and vector t transpose. So in the case when we're in the case of rank 1, we can say that xai is equal ua multiplied by vi. Remember, this is a vector. UA would be just a coordinate A of this vector, and VI would be I's coordinate of vector V. Those are numbers. So we multiply these two numbers, we get a number in our matrix X. So what intuitively it means if we're operating in case of rank 1? It means here that for each user, we are recording their general sentiment about the movies. So we can see that the first user has kind of lower ranks for the movies. Overall, his or her scores would be low, while the second user would be very optimistic. Similarly, when we are representing every single movie by one number, we are making this assumption this is how all the users like or didn't like the movies. So clearly, like, this movie had lower scores overall than this particular movie. Now you can say this is really oversimplification because we are now recording both the product and the user by a single number. It doesn't enable you to do what I suggested you doing in the first place, which is to take me, who has some preferences in machine learning and gardening. It will not represent me by two numbers. It's going to represent me by a single number. So in this case, if you want to have a richer representation of the user, you don't have to focus only on rank 1. You can, for instance, take rank 2. If you're looking at rank 2, now every user, this will be now not a vector, it would be a matrix U, and here we will have a matrix V. And here, let's say, a user may be represented by two different numbers. And these numbers may represent their opinion about the first class of movies and the second class of movies. And this similar thing will happen now with the movies. Instead of just having a single score for the movie, we will have two groups of the movies, kind of two aspects, how people like different aspects of the movie. So, and the higher you make the rank, the more multifaceted representation of the user and the movie you can have. And if we are successful and we did a good job in estimating our X in the factorized form, we would be actually able to identify these different groupings. And the number k of the, you can say, how do we know what is this k? Because I showed you, our whole discussion was focused on rank 1, but you can say maybe it's rank 2 or maybe it's rank 10. So typically you decide about k, the value k, on the development set. You would have development set, you will try various ranks, and you would select the one which gives you the best, the best evaluation number on the development. But for now, for this lecture, I will do you the computation for rank 1. Everything that I am telling you for rank 1 can be trivially scaled for higher ranks, and in your homeworks you would actually try it with higher ranks to see how it works. But again, the key idea would be exactly the same. So now we will start by taking our objective, the original objective that we had, which is written over here. We will take this objective and rewrite it for the case where our X is just a multiplication of two vectors, U and V. And once we've done that, our next question will be how we can actually find this U and V. Okay, so now we will take this objective and rewrite it as a in terms of our U and V, which are just vectors. So let's start. And I will keep the formula above so that you can see the connection. So let me start first writing that you remember that xai is actually equal UAVI, okay? Now we will take this objective that we previously expressed in terms of X and express it in terms of U and V, and again, remember that we make an assumption here that our matrix X is of rank 1. That's exactly what's written over here. So the objective now would look first we will compare the values that are present in matrix Y with our estimation. In this case, instead of writing it as xai, I will be directly expressing it in terms of ua vi squared, plus there will be terms that look at the norms of vectors u and vectors v. Previously, they both, we have vector x, we look at it as a whole. Now we separately control for u and for v. And so here we're going to go a from 1 to n, ua squared plus lambda divided by 2, I from 1 to m, vi squared. What I want to notice here, that if I estimated correctly all the u's and v's, it would be very easy for me now to actually estimate the function x. Even though I'm going to talk about only estimating u's and v's, you in your head should think that we're actually estimating matrix x, because when these two are computed, it will be trivial for us to take multiplication of relevant parts to get an x. Now let's look at this particular expression. The first thing that we want to say is that we are actually estimating here a function which depends on two elements, on u's and on v's. And estimation, because we have these two variables, it makes it a bit more complex. So what we will do here, we will again go to the iterative algorithms that we already seen in many portions of the class, where we will first select some of these variables. Let's say we will randomly pick up v, and then we will compute the u's, which are optimizing these objectives. Once we will select the new u's, we can go and to reevaluate the v's. So this will be an iterative algorithm that at each step of the algorithm we will set one set of variables, and then we will re-estimate another one. In order to see how this algorithm actually works, we will start with a very simple example. So assumes that I have a case of 2 users and 3 movies, and my original matrix Y has the following ratings. So what we see here, that for the first user, he or she ranked the first movie and the third movie, and the second user rank the first movie as 1 and the second movie as 2. So both of them have some values which are omitted. Our goal is to find u, which in this case, since we're making assumption of rank 1, it's a vector u1, u2, and v, which would be vector v1, v2, v3. So that is our goal. That's what we are trying to estimate, with the goal to minimize this objective. The way our algorithm will start, the first step, we will first make initialization. And in this case, my initialization would be to initialize vector v as, and I would look here, the initialization for which I did the computation would be 2, 7, and 8. Okay? This is my vector v. So the next step for me is actually to look at matrix X when we are computing the product between u and v transposed. So in this case, u vt would be equal to u1 u2 multiplied by 2, 7, 8. And what you will get here would be 2u1, 7u1, 8u1, and 2u2, 7u2, and 8u2. Okay? So this is your matrix X now. And what you're trying to do, you're trying to find u1 and u2 in such a way that this matrix would first of all have values for known entries which are close to what we have here, and at the same time controlling for the norm of the parameters. So what we are interested in, now we have our estimation, our matrix X. What we're interested in is to find the values of u1 and u2 so that the rankings that we actually observe that the matrix Y keeps would be close to what we have in our estimation matrix. And you can also immediately see that we can actually look separately at user 1 and user 2. Because we have separate rankings here, we can say, for instance, we want whatever is 2u1 is equal to, we want it to be close to 5, and for the same u1 multiplied by 8, we want to make it maybe closer to 7. This is our goal. We don't necessarily need to consider u1 and u2 jointly. We can separately do the estimation for u1 and estimation for u2. So that's exactly what we are going to be doing now. We are going to write our objective, this objective, for instance, for the first user. So for user u1, whatever we're going to write would relate to user u1. The first thing that we want to do, as I said earlier, we want to make sure that the observed ranking are close to estimated rankings. So we will do 5 minus 2u1 squared divided by 2 plus, we don't have any estimate for the second movie for this user, so we can immediately move to the third movie. So in this case, we are going to do 7 minus 8u1 squared divided by 2. So this part corresponds to the first term of our objective. Now we will move to regularization. So plus lambda divided by 2 u1 squared. So if we want to make our goal is to make this objective minimal, so we will do a standard thing that we've done before. We will take the derivative of this expression with respect to u1. And if you compute this expression, and I did this computation previously, what you will get here, you will get the following. You will get minus 66 plus 68 plus lambda u1 equals to 0. Okay? This will be the result of this derivative, and if we want to make it equal to 0 and we compute u1, you will get u1 is equal to 66 divided by lambda plus 68. So that's how we computed u1, which will minimize this objective. Similarly, we can do exactly the same computation for u2. We will compare for u2, how does it correlates to the rankings that we observed, plus the normalization factor. We will take the derivative, make it equal to 0, and if we complete this computation, which you will do as an exercise, you would get u2 equal 16 divided by lambda plus 53. So for instance, if we make our lambda to be 1, we will get for u1 66 divided by 69 and u2 to be 16 divided by 54. So let's notice what had happened here. Right now, we started with some random initialization of v. Then we computed u's which will be optimal with respect to this objective. So our next step is actually to take this u's and recompute the v's. Okay? So now our next step of our algorithm will be to take this u, 66 divided by 69 and 16 divided by 54. This is our use. And then we have our V's. V1, V2, V3. And again, if we will do this multiplication, we will get a new estimation of our matrix. 66 divided by 69 V1, 66 divided by 69 V2, 66 divided by 69 V3, and similarly 16 divided by 54 V1, 16 divided by 54 V2, and 16 divided by 54 V3. So now we have a new estimate of our matrix X. What are we going to be doing next? Taking this matrix and comparing it against Y that was provided, and do exactly the same computation, and the result of that computation would be new values for V1, V2, and 3. And we will continue this process until there is no change in the objective values. So we will continue until the convergence, and the questions that you may be asking yourself, are we guaranteed to converge? So what you are guaranteed to do a local convergence, but there is no guarantee to get to the global optima. And you can easily think about examples when, if we initialize incorrectly, we can actually get really bad results. For instance, when we start doing this process, we will select all the V's to be the same number, let's say to be 1. And it's a good exercise to consider what will happen in this case. So, but you can do several random initialization and select again the values which give you the best result on the development set. And again, once we are done with this process, let's say you did your random initializations, you tried them, you went through this algorithm, you estimated U's, you estimated V's, and the final result of it, that you actually now can fill in fully and completely your matrix X. And the computations that we've done in this lecture were all, for simplicity, done on rank 1, but exactly the same idea will translate to rank 2, 3, and K. And you will try it in your exercises. But what I would like to tell you that this very simple algorithm actually enables you in a very interesting way to find connection between different users and products, and given this very relatively simple machinery, you can actually solve a very non-trivial problem of product recommendation. So with that, we completed the lecture.